All right, let's play detective. Our case today involves an AI, and our mission is to unmask a very clever kind of digital imposter. A disguise so subtle, it's literally invisible to our eyes.
It's a pretty straightforward question, right? But the answer is, well, it's complicated. We're starting to trust AI with so much, from unlocking our phones to driving our cars. But what if I told you these incredibly smart systems have a hidden blind spot, a weakness that can be used to make them see things that just aren't there?
And this culprit? It actually has a name, an adversarial example. So picture this. You take a photo of a stop sign. Then you make these tiny, calculated little tweaks to the pixels, so small you'd never ever notice. And suddenly, a self-driving car's AI sees a yield sign instead. That's the invisible threat we're up against.
So in this explainer, we're going to dig into why this is such a big deal. Then we'll meet a new kind of AI detective designed to spot these imposters. We'll look at its toolkit, see how it did in a couple of very different tests, figure out why one test was so much harder, and finally talk about what this all means for building AI we can actually trust.
Okay, so why should we care? Is this just some clever academic trick? Absolutely not. This matters because these AI systems are leaving the lab and entering our everyday lives, where the stakes are incredibly high.
I mean, just think about it for a second. An autonomous car mistaking a pedestrian for a lamppost. An AI that helps doctors spot tumors, missing one because of a tiny digital glitch. Or your phone's Face ID getting fooled by a slightly altered picture. In these critical systems, a single mistake from an adversarial attack isn't just an error. It can have some really serious real-world consequences.
To fight this, researchers came up with a new method they call SECD. You can really think of it as an AI detective. And its strategy is pretty cool. Instead of trying to find the disguise itself, it looks for the weird behavior the disguised image causes in the first place.
The whole idea is actually pretty intuitive. It's basically guilt by association. If an AI looks at an image and says, "Yep, that's a cat," our detective says, "Hold on, let's see who it's hanging out with." It checks that image against a library of trusted pictures. And if our cat is surrounded by a bunch of pictures of dogs, well, that's a huge contradiction, a massive red flag.
So how does this detective actually run its investigation? Well, it doesn't just use one trick. It has a whole toolkit of techniques it uses to build a case against a potential digital imposter.
This diagram here shows you the entire workflow. A suspicious image comes in on one end, it gets run through a bunch of checks for these contradictions and other weird behaviors, and then a whole team of detectors gets together to vote on the final verdict. Is it real or is it fake? Let's break down what those steps actually are.
Okay, here's the breakdown. First, the detective finds the image's closest friends or neighbors from that trusted library. Step 2, it checks for contradictions. You know, like if the AI says, "That's the number 7, but most of its friends are pictures of the number 1. Third, it does something called feature squeezing. It messes with the image a bit, like reducing the number of colors to see if the AI's prediction is suspiciously fragile and changes easily. And finally, it takes all those clues and a jury of detectors makes the final call.
So the theory sounds great, but how does our AI detective actually do out in the field? The researchers put it through its paces in 2 totally different environments. And this is where the story gets really interesting.
The first test was on a dataset called MNIST. It's a simple, super clean world of black and white handwritten numbers. Think of it like a controlled lab setting. The second test, though, was on CIFAR-10. This is a dataset of colorful, real-world pictures. You know, cars, birds, dogs, the whole shebang. This is the messy, chaotic world outside the lab. A much, much tougher case to crack.
And the results were, well, they were dramatic. On that simple MNIST dataset, the method worked pretty well. It caught 54% of the adversarial examples. Not bad at all. But on the complex, real-world CIFAR-10 dataset, yikes, that number just plummeted to under 21%. That is a huge drop in performance.
These graphs here tell the exact same story. See on the left, for the simple stuff, the detection rate is high, and it even gets a little better as the attacks get stronger. But look at the right, for the complex images. Performance is way lower and it's basically flat. It can't tell the difference. And here's one more way to see it. On the left, that nice high curve shows the detective is great at telling friend from foe. But on the right, that curve is almost flat. That straight diagonal line represents just random guessing. It means the detective is barely any better than just flipping a coin. So what on earth is going on here?
So why? Why did our star detective do so well in the clean, simple lab, but struggle so much out in the messy real world? The answer, it turns out, is all about the fundamental difference between these two places.
Let's use an analogy. The world of MNIST is like a perfectly organized library. All the handwritten 2s are in one section, all the 8s are in another. Super neat. An adversarial image, a 2 disguised as an 8, it sticks out like a sore thumb because it's in the wrong section. But CFAR 10? Oh, that's a whole different story. It's like a huge, chaotic city. The dog category has everything from a Chihuahua to a Great Dane. There's just so much natural variety that an imposter can just blend right into the crowd without raising any suspicion at all.
And the data proves it. On CFAR 10, even totally normal, clean images only agree with their closest neighbors about 54% of the time. The adversarial ones, they agree 48% of the time. That difference is so tiny, they're practically indistinguishable with this guilt by association method. The imposters are just way too good at blending in.
So, what does this all mean? Is the method a failure? No, not at all. Actually, the most important part of this whole research paper might not be the method itself, but how honest the researchers were about its limits.
This quote from the paper really says it all. The authors are incredibly transparent about the challenges. They don't just show you what works, they show you why and where it fails. And that kind of honest reporting, that's how real science moves forward. So, what are the big takeaways here? First, these adversarial examples are a serious threat, no doubt about it. Second, clever ideas like checking for contradictions can work beautifully in simple, orderly worlds. But third, and this is a big one, the chaos and complexity of the real world make this problem so much harder. And finally, real progress in science comes from being honest about what doesn't work, not just shouting about what does. And that leaves us with a final, really important question. We are building our future on top of these incredibly powerful AI systems. But if we know they have these fundamental blind spots, that they can be tricked in ways we can't even see, how do we build systems that are truly safe, reliable, and actually worthy of our trust?